Hello, my name is Nathan, and I will tell you about worst case to expander case reductions. This is a joint work with Amir Abboud. Our motivation is something called the expander decomposition method. It's an algorithmic technique that was used to achieve many breakthroughs in the recent years. For example, decremental approximate SSSP, computing a Gomori Hue tree, approximate max flow, and dynamic minimum spanning tree. This technique was so strong that it managed to reduce large polynomial factors from what was the best upper bounds. Before I define what it is, I have to define you expander graphs. So we say that a graph G is a phi expander if for every non-empty cut S, such that the volume of S is less than or equal the volume of its complement. Volume means simply the sum of the degrees. So for every such cut, we have that the number of outgoing edges, denoted by E, is at least phi fraction of the volume of S. Now, we can simply look at the picture. It means that the total number of edges which are incident to S is not much larger than the number of outgoing edges. Now, we refer to this value, phi of S, as the conductance of S. And the conductance of a graph G is the minimum conductance over all such sets. Now I want to tell you about the expander decomposition theorem. It says that for any graph G and a parameter phi between 0 and 1, we can partition the vertex set of G into V1, V2, up to Vk, such that the induced subgraphs are all phi expanders. These are the clusters that we see in the picture. That the total number of edges between the subgraphs is small, is only phi times m times polylog factor, which I'm hiding. And we can compute this partition in something like m over phi squared time. Now, let's say we want to solve some graph problem A. The expander decomposition method says that given a graph G, we can decompose G into phi expanders using the expander decomposition that we saw. Then run some computation on each expander GI to obtain the solution for GI. This is the step where we can actually gain a speed up, because here we can utilize the properties of expanders, and some process might actually run much faster on a graph if it's an expander. And finally, run some computation on the remaining outer edges, which is kind of small, and then combine all the solutions together to get an answer for the original graph G. So that is the expander decomposition method. So we investigate the following intuition that says that all problems are as easy on worst case graphs as they are on expanders. When I say all problems, I mean natural and fundamental problems like maximum matching, K-click, for cycle detection, and more, which we also do not know how, if they even can be solved in linear or near linear time. So these are the interesting questions that we have in mind. And the first question that we ask is whether this intuition is true. Now, if this intuition is true, it means that it's enough to solve a problem on expander graphs. And then we also get the solution for any graph. And that's what makes many people believe that perhaps the expander decomposition method, seeing all the recent results, is the key to resolve all those remaining open problems. And that's the second question that we come to investigate in this paper. So to answer the first question, we need a way to reduce worst case instances of a problem into expander graphs. We could, of course, try to apply the expander decomposition method because that's what it does. But we suggest to take a step back here and start with a simpler approach. We define something that is called direct worst case to expander case reductions. This is the most simple form of a reduction we can think of. It's an algorithm that's given a graph G, outputs a graph G prime, such that G prime is an expander. The solution to G can be easily computed from the solution to G prime. And finally, the blow up in the number of vertices and edges in G prime is small. And when I say blow up, I mean that simply the size of G prime is about the size of G up to some polylog factors maybe. When we design such a reduction, ideally we want to obtain a conductance that is constant, and we want the reduction to run in near linear time. The reason why such reductions are interesting is because if the problem admits such a reduction, it means that the worst case instances of the problem are expander graphs. So first we get a positive answer to the first question. And secondly, it means that the expander decomposition method is useless against this problem. Because why would we try to apply expander decomposition if we can already assume that the graph is an expander? The expander decomposition might as well simply return the graph itself. So we get a negative answer to the second question. So the first part of the talk is dedicated to this kind of reductions. And we will start with two fundamental problems: maximum matching and triangle detection. So the maximum cardinality matching problem is to find the maximum cardinality set M such that no two edges in M intersect. The best upper bound is order of M times square root N, obtained by the Micali and Vazirani algorithm. I want to remark here that on random graphs, the Micali and Vazirani algorithm actually runs in near linear time. The second problem is the triangle detection problem, where we want to detect if G contains a triangle or not. The best upper bound is order of the minimum between N to the omega and M to the 2 omega over omega plus 1. Omega is the exponent in matrix multiplication algorithms. It's at least 2. And again, I want to remark that on random graphs, it's actually not very hard to see that we can solve this problem in strongly subquadratic time. The reason why I am mentioning the results on random graphs is because perhaps we can also solve these problems efficiently on pseudo-random graphs, like expanders. And then maybe we can also use, for example, the expander decomposition method to obtain a breakthrough to any graph. So this approach will actually fail because we managed to show direct worst case to expander case reductions. Let's start with the basic expander construction. This is a construction that we use in many of the reductions. And it's a very simple one. Given a graph G, we want to construct an expander graph G prime. We will add an expansion layer U. This is just a bunch of something like n vertices. And then we're going to add edges in the following way. For every vertex in G, we're going to sample the degree of V vertices from U. That this is a random process, and add the edges to them. So it's not hard to see that the number of added edges is order of M. It's simply the sum of the degrees. And we prove that assuming that the degree of every vertex is at least, let's say, 100 log n, then with high probability, the conductance of G prime is a constant. I want to note that we can also deal with graphs where there are vertices of small degree. If the degree of a vertex is smaller than 100 log n, we will just sample 100 log n vertices from U instead of the degree of V. Then the blow up might become n log n, the blow up in the number of edges. Let me just tell you the idea behind the construction. Why will this graph be an expander? So I think it's best to think about random walks. Let's say at some point in time, the random walk in this graph is on a vertex V in G. Then it has a probability of at least half to escape to U. And where does it escape to you? To some random predefined neighbor. So these works, they should mix well, and therefore the graph is an expander. Let me now tell you how we can use this construction to obtain a reduction for maximum matching. So first of all, we take the graph, we add an expansion layer U using the basic construction. The problem here that the MCM of G prime might not be fixed. Maybe it might differ depending on the randomness. So to fix that, we'll add a twin vertex U prime to every vertex in U. Twin is simply a degree 1 neighbor. And then it's not very hard to see that the MCM of G prime is simply the MCM of G plus U. Because all those new edges, we can assume that they participate in some maximum matching, and therefore the edges between G and U do not. So then the rest of the maximum matching is fully contained in G. And also with high probability, the conductance of this graph is still a constant, because by adding those neighbors, we did not ruin the expansion a lot. So we obtained the following theorem. Maximum cardinality matching admits a direct worst case to expander case reduction. So this problem is as easy on worst case graph as it is on expanders. And the expander decomposition method is useless against this problem. So we get a negative answer to the second question. What about triangle detection? Can we do something similar? So here we're going to assume that the graph G is tripartite, and also that every vertex has the same number of neighbors in every part except its own. We can assume this because we can always take any graph and take 3 copies of the vertices of G, and then add a copy of the edges between every pair. So the number of triangles in this new graph will be 6 times the number of triangles of the original graph. And the reason why we need this assumption is because the sparse cuts in this graph have a very specific form. They must have about the same volume in every part, meaning that the volume of S intersection VI is theta of the volume of S. Again, this is just because every vertex in S has the same number of neighbors in every part. So the construction is to pick an arbitrary part, let's say V2, and add an expansion layer only that is adjacent only to V2. We can see that it doesn't add any new triangles. It's simply, we only added a bipartite graph. And also the expansion of this graph is good. Because again, if the cut is expanding in G, we are done. And if it's sparse in G, it must contain a lot of volume in V2. And then it expands between V2 and U. So we obtained the following theorem that says that triangle detection admits a direct worst case to expander case reduction. And again, we get a positive answer to the first question and a negative answer to the second question. The next problem that I want to investigate is the 4-cycle detection problem. The goal here is to detect whether G contains a 4-cycle. Let me tell you about the complexity of it. So if the graph is 2 dense, let's say if M is at least n to the 1.5, then actually the graph must contain a 4-cycle. So the problem is trivial in this regime. But for smaller M, the best known upper bound is order of M to the 4/3, which is order of n squared. And there is a very recent lower bound of M to the 1.1, assuming the hardness of triangle detection. So I think it's a very intriguing gap to try to resolve. And maybe we can, maybe here the expander decomposition method might help us. So let's see if we can design, let's say, a direct worst case to expander case reduction for this problem. We're going to take the graph G and add an expansion layer U. The problem now is that we might have added 4 cycles. if two vertices in G had a common neighbor, and now they also have a common neighbor in U, then there is a new for cycle that did not exist in G. So there is a solution for that. Just subdivide all those new edges between G and U. And now every for cycle in this graph is fully contained inside G. But there is a problem with this approach, that the blow-up in the number of vertices is huge, because there are about m edges between G and U, and we added a vertex for every edge. So the theorem that we get here is that although for cycle admits a direct worst case to expander case reduction, the blow-up is very large. So we don't really get a definitive answer to question 1, because it is possible that we can solve a problem on expanders slightly faster on dense, let's say on dense graphs, and it will not tell us anything about the complexity on general graphs. And again, that also doesn't mean anything about whether the expander decomposition method will help us to resolve this problem. So that's actually what we're going to try to do now. We'll try to attack this problem through something called expander decomposition-based reductions. These are the reductions that we started with in the expander decomposition method. I just want to note that they have some shortcomings. For one, they produce, although they do produce phi expanders, the value, the conductance phi is limited to some 1 over polylog n. This is because of known limits to expander decompositions. So we cannot expect, for example, to prove hardness to true expanders or the conductance is a constant. And also they rely on heavy machinery that is involved with the expander decomposition. Compared to the previous reductions that we saw, this is less desirable. Anyway, we have no choice. We did not manage to show a direct worst case to expander case reduction for 4 cycles. So let's try to use the expander decomposition. Given a graph G, let's decompose G into n to the minus epsilon expanders, where epsilon is some sufficiently small constant. I want to note here that the number of outer edges is about phi times m. And because m is bounded by n to the 1.5, we get n to the 1.5 minus epsilon. Now, all we are left to do is only check if there is a for cycle that uses an outer edge. And in the paper, we managed to show that it can actually be done in strongly subquadratic time in n to the 2 minus 0.5 epsilon. So that's the whole reduction. The total running time is the time it takes to decompose the graph. That's the first term. And the time it takes to check if there is a for cycle that uses an outer edge. That's the second term. For any epsilon that is less than 0.25, we obtain a strongly subquadratic time. So the theorem that we get for cycle is that it does admit a worst case to expander case reduction. First of all, it's to n to the minus epsilon expanders. It's not bad. Epsilon is arbitrarily small, so anybody who can come up, say, with an algorithm that solves for cycle on n to the 0.01 expanders, it will also get similar results on general graphs. So I can say that we do get a positive answer to the first question, but we do not get a definitive answer to the second question. Let me tell you a little bit about some results that we have about exponential time problems. We consider the minimum dominating set problem and the minimum vertex cover problem. The question here is, what is the smallest constant c such that we can solve the problem in c to the n time times some poly n factors. The problem that we face when we design reductions for such problems is that we cannot afford an expansion layer of size n. It's too expensive. So for vertex cover, we do manage to use an exponential layer that has size order of log n. And for dominating set, we do the same, but size epsilon n, where epsilon is any constant. And the conductance of the resulting graph is some poly epsilon. We also have some interesting take about parameterized complexity of vertex cover. We managed to also control the size of the solution. It might increase by only order of log n. So the hardness here holds even against parameterized algorithms. Let me conclude the talk. We showed that many problems do admit direct reductions, maximum cardinality matching, K-click, subgraph isomorphism. This part is in the paper, or when the graph is sparse, minimum vertex cover, and minimum dominating set. In particular, it means that the worst case instances are expander graphs, and the expander decomposition method is useless against them. For 4-cycle detection, although we do obtain a reduction to n to the minus epsilon expanders, it uses the expander decomposition method. So we get some partial results. Let's conclude with some open questions. First of all, can we improve the reduction for 4-cycle? Find, say, a direct reduction to omega-1 expanders. I think that another interesting problem is the max cut problem. Here, I have a feeling, I think there is a good chance that actually this problem will turn out to be easier on expander graphs. And also, what about other models of computation? This technique is useful not only in the sequential model. So what about reductions in dynamic, streaming, distributed, or sublinear model? What about other notions of pseudo-randomness? So, for example, can we design reductions to semi-regular graphs or p-beta jumbled graphs? These are known notions of pseudo-randomness in graphs. And finally, why restrict ourselves to graphs? Maybe we can provide such reductions to pseudo-random strings or pseudo-random sets or any other objects of interest. So thank you for listening.